So now we're going to talk about relative motion examples in 2 dimensions, also known as the sequel to one-dimensional motion. Alright, so here's a simple 2-dimension problem. We've got a person going on a river. Now, velocity is a vector, so what we're going to have to do, we're going to have to break this into components. But first, let's talk about what these components are. So we've got this person swimming, and this river right here. What's the person swimming in? The river. So the velocity of the person to the river equals 3 meters per second. And I'm going to say this way, in the x direction. What's the river relative to? Well, the river is relative to the Earth. So velocity of the river relative to the Earth equals negative 4 meters per second. Y hat, because it's going down. And the question is asking you, what's a person on the shore? So you need to solve for the velocity of the person to the Earth. So how would we set this up? Let's take a look. And we have to break this into components. So what we would know is overall vectorially, this would be the velocity of the person measured by the Earth equals the velocity of the person with respect to the river plus velocity of the river with respect to the Earth. Alright, and these are vectors. Whether it's a vector means you have to break it up into components. So we get, so V, P-E-X equals V, P-R-X plus V, R-E-X. In this case, does the river move in the x direction? Nope, only goes in the y direction. This one goes to 0. So this is going to be equal to 3 meters per second, because the person in this case is only swimming in the x direction. How about the, let's do the y components now. So we know V, P-E-Y equals V, P-R-Y plus V, R-E-Y. This is 0 because person's only going the x direction, so we get negative 4 meters per second. So now you have x components, y components. To find the total magnitude of the velocity v person to the Earth, this is equal to the square root 3 meters per second squared, just Pythagorean theorem squared, plus negative 4 squared equals 5 meters per second. And then you need to solve for your angle. So theta equals tangent negative 1 y over x. So in this case it is negative 4 over 3, which is equal to negative 53 degrees. Didn't mean to move that, meant to have the pen. Negative 53 degrees. Now you have direction, you have magnitude, you have all the components for a vector. And now there's one last example. In this final problem, we have a plane. The plane is going east, but we see it going this way, 25 degrees south of east, or negative 25 degrees. This is a vector problem, so we have to break it into components. So what we are originally trying to find, we are trying to find the velocity of the wind relative to the Earth, and I've labeled it air relative to the Earth. The plane is traveling in the air, going 400 meters per second east. This is like the person swimming in the river. The plane relative to the Earth is 425 at some angle. So let's talk about what we need. We need this, if we're building our general equation, you want a to the Earth. Why don't you take a moment, try to match the indices, see what you can do, and see what you can think of. I'm going to wait here. Okay, so when we're talking about putting this together, we got the velocity, hold on, I'm going to grab a blue pen real quick. The velocity of the plane to the Earth equals the velocity of the plane to the air plus the velocity of the air to the Earth. This is the crosswind that we are trying to solve. So let's rearrange this and we'll move this to the other side, this being the velocity of the plane relative to the air, and you get velocity, plane, relative to Earth, minus velocity, plane, relative to the air, equals the velocity of the air relative to the Earth. All right. And I put the little arrows here indicating that it is a vector. So let's break this into components and solve for it. So we have our equation here, our vector equation. Let's break this up into components. Like so, just as we've been doing in class, you make an x set, you make a y set. So let's plug this in. So you know that VAE runs this way, so if we break it into x component, y component, this is your angle theta. Our x component is going to be cosine, so this is 425, because that's what the observer on Earth sees, 425 cosine. I'm going to use negative 25, because that's the angle. And since I'm measuring from the x-axis, the sign's going to get taken care of, minus 400, because 400 is the x direction for the plane relative to the air. This was its flight speed. The plane flies in the air. So now if we do this, we're going to get negative 15 kilometers, that's a bad K, kilometers per hour. Similarly, if we work the y direction, instead of cosine now, we're going to use 425 times sine of negative 25 degrees minus, well in this case it's 0, because the plane's not flying up or down, it's only flying to the right. Up or down would be north-south in this case. Good. And then we'll find out that this is equal to negative 179.6 degrees. Now because this is a vector, we need to find the magnitude of AE, which means we need to use our Pythagorean theorem, because it's fantastic, minus 15 squared plus negative 179. That's a degree sign. Let's get rid of that. That doesn't need to be there. That's kilometers per hour. Sorry about that. Just noticed it. 179.6. I apologize if that extraneous degree sign caused undue stress. So when we square this, we get 180.2 kilometers per hour. But we're not done, because our answer is a vector, so we have theta equals tangent inverse y over x, so negative 179.6 over negative 15 y over x, which equals 85.2 degrees. If we notice, if our components are negative, that means we're going, let's see, x negative 15 and this way, which if you can see, this is not negative 15. So what do we have to do? That's right, add 180 plus 180 degrees. The evil tangent strikes again, and we get our final angle at 265 degrees. Well, I hope that's been helpful, and if you have any other questions, shoot me an email, stop by my office, and I will see you later.